So what I have here in front of my screen, hopefully that you can see, is a table that has the so-called prefixes that the metric system, and in fact any system, can use. These prefixes simply tell you a multiplier that applies to the base unit of the system that you're dealing with. So in the International System of Measurements, which I'm going to be just calling it the metric system, although they're not identical, for length we use a meter. So anytime you see a prefix from this chart in front of the word meter or the symbol lowercase m, that means that you have to multiply the base unit by a factor indicated in this chart. So if we have 1 kilometer, so it has the little k in front of it, that means that in meters, the base unit, we have 1 meter times 1,000. So we have 1,000 meters in 1 kilometer. If you're talking about a megameter, then you need to multiply, if we have 1 megameter, we multiply the 1 by 1 million, and that's the number of the base unit, 1 million meters in 1 megameter. And so on and so forth. Now, the reality is that many of these conversions, you can let your calculator or even Wolfram Alpha, which we'll probably try to use again today, you should let them do the conversion for you. But you should also know that you can set up conversion factors. And that's where we're gonna start right now. So let me switch to my camera and show you what I mean by that. Where is, okay. Let's stop sharing and switch. Now these conversion factors are extremely useful for not only this course, but I would even argue for the rest of your lives. I use these things in the kitchen all the time if I'm trying to reduce a recipe, not by half, but by some other fraction. So let's make first sure that we are all understanding. Well, we're gonna call these our conversion factors. And sometimes this is called dimensional analysis because we analyze the dimensions that we are working in. And let's start very simply, very simple. Let's start by saying, okay, so in the chart that we were looking at, we learned that 1 kilometer or 1 kilometer contains 1,000 meters. So that was from that chart. This equality is the starting point for creating conversion factors. And from every equality, you can get 2 conversion factors. Now, this is telling you that 1 kilometer is exactly the same as 1,000 meters. So we don't worry about significant digits when making conversions, but we do worry about significant digits in the numbers that we have to convert, not in the conversion factors, but in the numbers that we have to convert. Now, let's first take a look at the 2 conversion factors that come out of this equality. One looks like this: 1 kilometer divided by 1,000 meters. So that's a conversion factor. And the interesting thing about this is that if you were to really divide this distance by that distance, you get 1 because it's exactly the same. So when you use conversion factors, you are getting to multiply or to divide by these big numbers or by small numbers. But in reality, you're not changing the amount, you're just changing the dimension. So if we're gonna go from the dimension of meter to the dimension of kilometer or vice versa, and that is because that divided by that is 1, but it's really not 1 if you think about it. If we remove the kilometer and the meter, then of course 1 divided by 1,000 is 0.001. That's a real number. we need to always keep the units associated with this conversion factor, or we are making a mistake. Now, the second conversion factor that comes out of any equality is the reverse of the first one. We just flip the numbers and we have 1,000 meters divided by 1 kilometer. So those are the two conversion factors, and that's always the same for any equality. Only two conversion factors possible. Now, how do we use these conversion factors? Well, let's say that we have the task of converting 2.932 kilometers to meters. That's the question that we want to answer. Now, obviously, in this case, it's quite straightforward. For some of you, it's going to look really simple, but we're going to do the process anyway. So the first thing to notice is that we have the units kilometers or kilometers, and we want meters. So we need to know where we come from and where we're going to. Because that is going to determine your choice of the conversion factor. Now, some of you who have done this before, or who may remember having done this in another class, don't change a thing if you already know how to do it. But if you don't, I'm going to be emphasizing that we need to choose one of the two conversion factors by thinking multiplication. I know you're going to be thinking, well, we're really dividing, but just bear with me and you'll see what I mean. So what we're going to do now is I'm going to copy that number again, 2.932 kilometers. And I'm going to put a parenthesis because I want to multiply that number by one of these two conversion factors. So which of the two am I going to choose? Well, I'm going to choose the one that has the units that I want at the end on top. So the units that I want at the end are meters. This conversion factor here on the right has meters on top. So that's the one that I'm going to bring down and copy here. 1,000 meters divided by 1 kilometer. And that's the conversion factor that I'm going to multiply by the original number. So now I just carry out the arithmetic, and notice that when we carry out this operation, this is a fraction that is written as an integer, meaning I can imagine that on the bottom of that there's a 1. In other words, I can convert that into a fraction that looks like this. I have changed nothing except just imagine that that's a fraction. And why is that helpful? Well, because I'm going to be having a numerator and a denominator. And the numerators are divided by the denominators. So kilometers are divided by kilometers here. And what I hope you become familiar with very quickly is that if there's kilometers on the top and there's kilometers or kilometers on the bottom, and you divide them, you get 1. And that's what we call canceling out. So kilometers and kilometers cancel out if they are on top and the bottom. If they're both on the bottom, remember what we did last week. We multiply them and we would get kilometers squared. So that's one way to check that you are getting the right units. If I had chosen the other conversion factor, I would have kilometers on top and I would be getting kilometers times kilometers, kilometers squared. So that would be wrong. But if I do it right, what I get here as units is meters because the kilometers are gone. And then I just multiply with my calculator 2.932 by 1,000. I'm going to get 2,932. And now let's talk about significant digits. This conversion factor doesn't matter. We don't consider it when we don't take into account the conversion factor when counting significant digits. because it has an infinite number of significant digits. According to our equality, 1 kilometer is exactly 1,000 meters. So the only thing that counts is this guy. This has how many significant digits, anyone? I'll get an answer from one of you if you don't mind unmuting yourselves. How many significant digits on that number?
4.
4. So we're gonna say 4 significant digits, thank you. The answer has to have 4 significant digits. So if you want, you can write it like that. You can add a comma just to make it look better, or you can even add a decimal point to emphasize the fact that you have only 4 significant digits, but you don't have to. And that would be your answer. Now, what if we wanted to convert the opposite, meters to kilometers? So let's do that. Now we're gonna have, I was gonna use the same number, but I better not. We have simply 451.2 meters, and we wanna convert that to kilometers. So as you can imagine now, we need to choose the other conversion factor. And again, you choose a conversion factor that gives you the units that you want to keep on top, or that has the units that you want to keep on top. And I'm gonna emphasize the fact that I'm saying multiply. So I'm multiplying by a conversion factor. In reality, when you do this on your calculator, you're dividing by 1,000. You are correct in thinking that. But in the way in which I'm describing this, I'm saying I'm multiplying by a conversion factor. And I will always say that. So my equal sign, I can see here that meters cancels with meters, because meters on this number is in the numerator, here is in the denominator, so they divide by each other, giving me 1. That's the same thing as canceling. And now I multiply 451.2 by 1, but then I divide by 1,000, because this is a denominator. And what that gives me, unless I make a mistake, is 0.004. Oh no, wait a minute. I'm making a mistake already. 0.4512 km. Now let's talk about significant digits. This number right here has 1, 2, 3, 4. This number has to have 1, 2, 3, 4. This is just a placeholder. And that would be the answer. So, any questions up to this point from anyone? We're gonna move on to do a couple more examples, and then we're gonna switch gears and talk about converting between systems. So let's say that we wanted to convert this answer that we have here, 0.512 kilometers, to, and let me switch very quickly to choose something appropriate here. I'm not a fan of Zoom and how you can just simply switch. Maybe I should be sharing my desktop instead of my browser. So let's choose one here with scientific notation. So for instance, giga. I'm pointing at the G here, and we are seeing that the giga prefix is 1 times 10 to the 9th base units. So 1, my goodness, that's a million. That's I guess in the US is a billion. In the rest of the world is a million. No, it's 1,000 million. This is a billion, by the way, in the rest of the world. Here in the US, it would be a trillion. But I don't want to confuse the matter. It's just that I know many of you come from different countries sometimes, and they use different words for that. So we're not gonna call it billion. We're gonna say 1,000 million. Or better yet, 1 times 10 to the 9th. So that's what we're gonna do. Let me see, convert to giga. meters. I'm gonna switch now to my other screen. And let's see if we can try to do the conversion. Now, you're here, therefore I assume that either you are having the time to be here, or simply you want to take care of these as quickly as possible and get over with the course. These meetings are not mandatory, so I want to emphasize that for anybody who is not here. But if you get frustrated by the pace at which I am covering this material, please don't be. We'll speed up eventually. Right now, I just have to say the following. I need to write an equality here. And I'm going to write it backwards. I'm going to say 1 meter equals 1 times 10 to the 9th. Sorry, I made a mistake. 1 gigameter equals 1 times 10 to the 9th meters. I don't have a way of erasing that, so let me write it one more time. Now notice one thing. We are dealing with kilometers here, and we don't have a conversion factor for that. We don't have an equality for that. So when we do this by hand, you need to do it either via 2 stops, or you can do what some websites and some tutorials on the internet may show you. And it goes something like this. King Hector died of an overdose of chocolate, something stupid like that. You probably think, what is he talking about? This is not English literature. Well, I'll show you what I'm talking about in a few minutes. First, we're gonna actually just solve the problem the slow, old-fashioned way, and then I'll show you what some of your classmates in previous courses and through history have done to solve these problems faster. So we need 2 equalities here. We need that, and we need the one that we have on top. So I'm not gonna write it down again, but I'm gonna do this in 2 steps. So let's start. We have 0.4512 kilometers. And we want to go to gigameters, but we don't have a conversion factor that takes me straight to gigameters. So first I need to convert kilometers to meters. I know that from the previous example that I can choose one of these 2 conversion factors so that I change the kilometers into meters. So I'm gonna choose the one on the right because that's gonna cancel out the kilometers. So I put here 1,000 meters divided by 1 kilometer. But I'm not done yet because we want gigameters. Now, notice that this is gonna cancel with that. So now we put another parenthesis and we look at this equality. Let's scratch that one because it's confusing. We look at this equality. And from that equality, you can get 2 conversion factors, just as we did before. One with the gigameters on top, one with the meters on top. As I told you before, we want to choose the one that has the units that we want at the end on top. So we're going to choose the 1 gigameter on top. So I'm going to put 1 gigameter divided by the other unit on the bottom, 1 times 10 to the 9th meters. And magically now, meters cancel with meters, and the only units that we have left are the gigameters. So if we carry out this operation, we're gonna end up with our answer. So first we multiply by 1,000, then we divide by 1 times 10 to the 9th. I'm gonna give you 30 seconds to see if you guys come up with an answer while I do the same operation here, and then you tell me what the answer may be. And I'm just doing it one step at a time without trying to take shortcuts.
451.2.
451.2. 451.2. I hear from someone. I have a different number.
Oh, I did it on the scale.
You did it on the scale.
Yeah, the ladder.
Oh, I see. The King Henry or whatever.
King Henry died unexpectedly drinking chocolate milk.
Well, this time King Henry didn't help because I have a different number.
We're going what, from kilo to regular units, right?
We're going from kilo, yes, from kilo to regular units. You're absolutely right. But we're going all the way to gigameters. So we're going from kilo to gigameters.
Oh, okay.
You use King Henry. If it works, I really want you to show the class, Suzanne, how you do it. But it's not 2 meters. In the screen, what you see, unfortunately, is the long way to do it. The way that some of you don't like to do it because it takes time, is too confusing. So you go to King Henry, and I don't know him, so I don't know how to do it that way. And you do it in one step. So give it another shot, Suzanne, and then tell me what you think you find the answer is. But if anybody did it the old-fashioned way, this way, this is not the answer. That's just the answer to these first two parts. I really wish I knew better how to use that ladder.
So is it 451,200?
I have a small number on my screen, on my calculator. Let me show you what I have on my calculator. That's what I have on my calculator.
Yes.
0.00000045. And I'll put that in a second in scientific notation. But
So, it's 4.512 times 10 minus 7.
1, 2, 3, 4, 5, 6. Yes, to the negative 7. Or 0.00000004512. And the units, we better not forget, gigameters. That's the right answer, everyone. And I want to go to King Henry and see if I can figure out how that works. But in the meantime, I have to tell you.
King Henry gets confusing when you have the giga and the mega.
I know.
Because you got to move extra. There's 4 extra spots you have to move there. It really doesn't show.
Right.
So it kind of gets confusing there.
Yes, it does. And that's why I have really never spent the time myself to learn how to do it. It's very nice because it's a ladder that visually tells you how to do it, but you're not thinking. You're just moving the decimal point mindlessly. You see what I'm saying? In this approach.
Right, and it got me caught up doing some of the exercises too, so.
Oh, I see. Well, if you follow this approach, you can see if you make a mistake because you're analyzing the dimensions every step of the way. And as long as you don't make a mistake entering the numbers in the calculator, the answer is always going to be right. It is time consuming and it does take an extra thing to learn. But once you know it, I can assure you, you'll never make a mistake this way, the way the chocolate drink thing does. So let me go to the, I guess the homework. Let's see what we have, or even the quiz in this type of problems. So homework. I'll share this with you in just 1 second. Let me just find where I'm gonna go. Okay, here we go. So I think we did this last week. Let me just start skipping. Oh, wait a minute. No, what I'm talking about. This I haven't. Okay, hold on. Let me go back. Yeah, so this we haven't done. Okay, so let's start easy, and we're lucky to have this first question. Can you guys see my screen?
Yes.
Is it big enough for you to read, or is it unreadable?
Can you just enlarge it just a little bit? Because I'm
Yeah, let me see how that is done. If I make my screen smaller here, did anything change for you guys?
a little bit.
Okay, so now let me try
Yeah,
something
that's
else.
fine.
Does that do anything?
Yeah,
Good, yeah.
yeah, that's perfect.
Okay, let me just.
I think in this one they have a mistake.
Oh, really? Okay, I want to know always our mistakes. I love catching them making. So they're not God, they do make
Yeah.
mistakes. So in this problem, you think, Amal, or is it a different one?
Yes, in this problem, yes. Because I know 1 gram equals 1 times 10 to the 9th. But in here, we have 1 gigagram. So it's gonna be 1 times 10 to negative 9 gram. But they put the answer is to positive 9.
Let's see. Well, in this case, I don't think there's a mistake because the giga unit is huge compared to the gram unit. So there's going to be a lot more grams.
Yeah, but 1 gram equal 1 times 10 to the 9th. 1 gram.
Right. 1 gram equals 1 times 10 to the negative 9 gigagrams.
To the negative. Okay, yeah, so I'm
You see what I'm
confusing.
saying? If we put the big G, if we move this big G to this side,
Yes.
and we leave the little g by itself, then you're absolutely right. 1 gram equals 1 times 10 to the negative 9 gigagrams. But
Okay.
the way it's written, that would be the right answer.
Okay. Yeah.
Yeah, take a closer look. I mean, it's very easy to get confused, and I get confused all the time because, I mean, I really hate that chart, and I just use it to create conversion factors. Reading it, I've always make the same assumption that you were making, but I think in this case, this is the right answer. So let's, and I'm supporting the answer. So even though I said they were not gods. Now, let me go to the next one. And then according to the metric system, 1 second equals nanoseconds. Let's do this. And since I don't have the book open, well, actually I have it right here. Let's take a quick look at this and just make one general comment. The units on top of the base unit are units that are bigger than the base unit. In other words, a tera, a peta, a giga is going to be much bigger than the base unit of the meter, gram, or liter. And then the units on the bottom are tiny, tiny units. In other words, one of these is going to be even less of one of these. In other words, one of these is many of these because these are tiny compared to these, and these are big compared to the base unit. So going back to the question here, where is it? Immediately think to yourselves, is this a tiny unit or is this a big unit? Well, it's a tiny one. It's called nano. It's right here, and it's 1 times 10 to the negative 9 of the base unit. So it's 1 billion times smaller than the base unit. So when we go back to the problem, 1 second is going to have many, 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 many nanoseconds because the nanosecond is smaller. So there's going to be many, many of them in one of these. So that has to be this answer. Okay? If I switch it, if I say how many seconds in 1 nanosecond, then it would be 1 times 10 to the negative 9, but not as is written. So always double check and triple check your logic. It will pay off at the end of the assignment by reducing the number of mistakes that you make. So let's see here. Here they want for you to write a unit equation for the equivalence that you see here. And I quite frankly don't know how they want it, but they probably will accept scientific notation as well as decimal notation. But they do tell you what the base unit is going to be. In other words, they want you to answer the number of meters in 1 gigameter. And remember, gigas are huge. So there's going to be many meters in 1 gigameter. And we've been seeing that as, I'm going to enter as decimal first. 1, 3, 3, 3. I think that's a problem with decimal. That's a million, and that's 1,000 million, which is a billion. So I believe that's the answer. Anybody wants to check me? Would you agree with that?
Yes.
All right, so let's submit it. And I guess the system changed it to scientific notation. So let's do that going forward. So now we have grams and teragrams, and they tell you that they want the equivalency for 1 teragram, not for 1 gram. So going back to the table, the tera means 10 to the 12th, and it's a huge unit. So there's going to be many of the base unit in the tera. So many, this number has to be huge because the tera is much bigger than the base unit. And according to that, it was 1 times 10 to the 12th. Oops. So I just switched to this symbol notation, but I chose the wrong place to put it. This is 1 times 10 to the 12 grams equal 1 teragram, and we're gonna submit that. So let's take a look at this one. This one is interesting because now we're using a small unit, the nano again. So let's go back to the table. And we see that nano is much smaller than the base unit. 1 times 10 to the negative 9 meters are 1 nanometer. So going back over here, what do they want? They want the nanoliters. So there's gonna be many nanoliters in 1 liter because the liter is much bigger than the nanoliter. They're trying to trick you guys. This is the reverse from here. So let's see. One liter, what was it? 10 times to the negative 9. If these were the nanoliters, then this would be negative, but because it's the liter, there's gonna be many nanoliters in 1 liter. So we're gonna choose that and say 1 times 10 to the 9th, not to the negative 9, and submit that answer. I know this can get confusing, so just practice and hopefully it will become second nature. So let's do the last one. Picoseconds from seconds. Pico, oops, according to the book, is 1 times 10 to the negative 12 of the base unit. So 1 picosecond is 1 times 10 to the negative 12 pico seconds. What are the units here? Yes, seconds. So the opposite should be true. there's going to be many, many, many picoseconds in 1 second. So the negative 12 that we just saw there has to become a positive number. And it's going to be 1 times 10 to the 12 instead of negative 12. I repeat, because this is the base unit, and there are many picoseconds in one of the base unit. If this had been picoseconds and these seconds, then it would have been negative 12. I hope you have time to review this on your own, because it can actually be a little frustrating. Now, this is practice to write conversion factors. I think you can probably handle them without me going through each one of them. So I'm just going to look at the first one. So write 2 unit factors for each of the following metric relationships, meter and terameter. If I quickly look at the book, tera means 10 to the 12. Tera is huge compared to the base unit. So we're going to have many meters in 1 terameter. So if you look at the top one, here they're saying that 1 meter equals many, many, many terameters. And that's wrong. The terameter is bigger. So you have to have many, 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 many meters in the terameter. So it's going to be the bottom choice. Okay? Always double check yourselves that way. What is big and what is small, comparatively speaking. So I let you do the other 3 for practice on your own. And if you have any questions, please do stop by my office hours later, tomorrow, or I have office hours every day except Mondays. Now let's take a look at this. If a computer chip switches off and off in 0.015 microseconds, what is the switching time in nanoseconds? Well, we did problems like that in the introduction to this chapter. So I'm gonna let you do that. But I wanna just see one thing here. If I copy that into Wolfram Alpha, have any of you had a chance to experiment with Wolfram Alpha? If you have, maybe you know what is gonna happen when I paste this, but I haven't. So let me just put that number and hit enter without asking the calculator anything. So look what happened here. Wolfram Alpha converted the microseconds correctly to seconds. I don't even know if that's the question. Let's see. Oh, it's a trick question because this is micro and this is nano. So we had to do the 2-step dance that we did before, because first we had to go from microseconds to seconds and then from seconds to nanoseconds. There's no conversion factor unless you trust King Henry to go straight from microseconds to nanoseconds. I think there's a 3-fold difference, so maybe King Henry could help on this one. But let me see if King Wolfram Alpha can help even better. I'm gonna put in microseconds and see what happens. So it did the conversion for us over here, 0.015 microseconds. Wait a minute. Am I making a mistake, you guys? Nobody's calling my attention. To nanoseconds. Yeah, sorry about that. So I was getting the same number. 2 nanoseconds. Let's see if Wolfram Alpha is smart enough. Yes, it is. Look at that. There is the answer. 15 nanoseconds. It also gives you the answer in seconds still, but there is the answer in nanoseconds. So let's just, without even thinking, answer that based on Wolfram Alpha and see if it's right. And it is right. So quite frankly, if you know how to use Wolfram Alpha, use it to double check your answers before you use it to just do the problems without being sure if it's working for you. In other words, spend some time learning the technique that I show you on my camera. Once you feel comfortable with that, you can go to Wolfram Alpha and let do the heavy duty work for you so that you don't have to spend hours doing one single problem. But you do have to spend some amount of time trying to learn this on your own, the long old-fashioned way. Trust me when I say that. I've seen this before and it's better to do it that way. Okay, so let me move on here. And again, this is giving you a number in kilometers and it's asking you to go to megameters. So we're gonna do this the old-fashioned way, and then we're gonna ask Wolfram Alpha to do it for us, and then we're gonna take a quick break. So let me copy that problem, you guys, to my piece of paper, and then we'll start with that. Okay, I think I'm ready. So we're gonna try to convert 1.50 times 10 to the 8th kilometers to megameters. Again, we don't have a straight conversion factor for that. So we're gonna have to do this in 2 steps. Remember that we do know that 1 kilometer equals 1,000 meters. And we also know that 1 megameter equals, oh my God, I forgot. It was, I'm trying to quickly go to the book. I mean, mega times 10 to the 6th. Meters. Okay? Boy, this gets confusing when I need to be switching screens like that. So those are the 2 conversion factors that we need. And we need to do this in 2 steps, unfortunately. Now, if Suzanne, if you're still trusting King Henry, see if you can actually verify this answer when we finish. So we're gonna start 1.50 times 10 to the 8th kilometers. The first thing we need to do is go to the base unit, to meters. So we're gonna multiply that by 1 conversion factor coming out of this equality, and the one that has the units that I wanna keep, meters, on top. So 1,000 meters divided by 1 kilometer. Now, if I were to just stop here, I would have my answer in meters, but the problem wants megameters. So I need to keep going. I need to add another conversion factor coming from this equality, and I want the units that I want to keep on top. So I'm going to put 1 megameter on top, and on the bottom I'm going to put the equivalent in meters. 1 times 10 to the 6th meters. So many meters in 1 megameter. And now if I carry out the operation, I should have the answer. Let's look at the dimensions, at the unit dimensions. Kilometers cancels with kilometers, meters cancels with meters. So we set it up right. We did choose the conversion factors correctly from those equalities. We're gonna end up with megameters. And I would just do this on the calculator. And let's see, that's gonna be 11. I think it's gonna be 1.50 times 10 to the 5th, but I'm not sure. I am trying to do it in my head. I'll show you what I did in just a second, but I want confirmation from someone. If you can do this on your calculators, That would
Yes.
be awesome.
Correct.
It is correct?
Yes.
Okay, so I have one confirmation. I'm still trying to do it on my own. And I get yes. 1, 2, 3, 4, 5. Yes. Now, couple of things to notice here. The significant units that we need at the end have to be the same significant digits that we have at the beginning. I have a question, and it's not a trick question. How many sig figs are in 1.50? You need to be really good at it by now. There's a 0, but it's after a decimal point and to the right of a non-zero, so it counts. So I'll save you the time, and this has 3 significant digits. That 0 counts. So this has to be written exactly the same way, 1.50 times 10 to the 5th. And the units are megameters. We can go back and see what happens when we enter that in the homework. So I'm switching screens. Share. So is there one choice right there? Looks like that's the one. 1.50 times 10 to the 5th. You guys see that still? We're gonna go, okay, we're gonna go with that, submit it, and we got it right. Now, let's check Wolfram Alpha, and then we'll take a break. So we have 1.50 times 10 to the, and I think Wolfram Alpha likes this symbol, is the little symbol on top of the number 6 in most keyboards. I think it's called the caret sign. And then I'm gonna put the units kilometers, convert to megameters. And let's see what it does. And you know what, just for good measure, I'm gonna put parentheses here in front of the number so that I emphasize to Wolfram Alpha that that's scientific notation. Well, it looks like
No, to the 8th. You put to the 6th.
That's it. I was thinking it's failing us. All right, thank you for paying attention.
Yeah.
Yes, it did, except here's the big problem with Wolfram Alpha and with any calculator. We're still smarter. We humans are smarter than these devices. So here's the answer, and he's right. Okay? First of all, it's not in scientific notation. So you have to convert that to scientific notation. No problem, it is 1.50 times 10 to the 5th. The other problem is that doesn't tell you the number of significant digits. It's implying, it's ignoring that 0. You see how it didn't write it down here?
Yes.
So it's making a mistake. It's not perfect. That is up to you to realize. So the answer to be correct has to have 3 significant digits. And this answer has 2 significant digits only. So here we go again. Now, the conversion factor process or procedure that we just went over in the first hour works really well also for when you need to make conversions between different systems of unit of measurements. So I'm talking about the English system now. So the conversions that we did before were all metric to metric or international system to international system. Now we're going to talk about how to make conversions from the metric system into the English system and vice versa. And here there is actually no King Henry that drinks chocolate or whatever he did. We had to do it with conversion factors. Now, before we look at this problem that I have on my screen, I want to show you a table from your book that has some of the English metric equivalents that we're going to be using. This can get a little tricky because if you use a slightly different equality, you're going to get a slightly different answer. But I think mastering is good at recognizing the fact that some people sometimes use slightly different equalities. So it gives you a little bit of room when you make a mistake. But to try to avoid that, we're going to use these guys right here that we see on the screen when making or solving the problems that we're going to be addressing. So the first problem in the homework asks you to convert kilograms of water to liters of water. Oh, wait a minute. No, that's not true. It's stating that 10 kilograms of water occupies a volume of 10 liters of water. So this is basically a statement that is trying to distract you because it's not the question. The real question is, what is the volume in quarts? Well, this is not volume. This is volume. In other words, I can get rid of that part of the question and just say, what is 10 liters in quarts? That's the new question. What's the volume of 10 liters in quarts? So a little tricky there. Now to that, if we look over here, we have an equivalent of 1 quart into milliliters. And the problem talks about liters. So we have already an issue. Either we quickly convert these to liters in our heads, or we do the two-step that we've been doing before. I'm gonna do it both ways, just bear with me because it's going to show you that sometimes you can take shortcuts, but sometimes you can't. So let me switch to my camera and tackle that problem. Okay, so we need to convert 10, oops, sorry. Let me, forgot the number exactly. 10.0 liters to quarts. So that's the task. The book tells me, at least on that one chart that we were looking at, that 1 quart equals exactly 946 milliliters. But notice that I have liters, not milliliters. So what do I do? Well, either I create a new conversion factor in my head that expresses these in liters, or I do it in 2 steps. So let's first do it in 2 steps. 1 liter equals 1,000 milliliters. So we have 2 equalities, and we're gonna walk from liters to quarts using those 2 equalities. So as you already know, the first thing to do is put the input number and multiply it by the first conversion factor that is going to turn that unit of liters into milliliters, because then we can go to quarts. So from this equality, I want to create a conversion factor that is going to eliminate liters and is going to keep milliliters. So I put the milliliters on top and the liters on the bottom. And then I'm not done because I need to convert milliliters to quarts. So from this equality, I choose a conversion factor that has quarts on the top, because that's what I want at the end, and milliliters on the bottom. So 1 quart divided by 946 milliliters. And before we do the calculations, we look at the unit analysis, and liters cancels with liters, milliliters cancels with milliliters. So we know we set it up right because in the end we have no other units but quarts. And then we just do the math. And you have to be very careful because you have some multiplications here, but you also have some divisions. Although I've been setting this up as multiplications, they're fractions. So you need to remember that the denominator is always dividing a numerator number. So please follow along and do your own calculations. I'm doing them here myself as we speak. And then we'll verify our answers together. So I'll wait until one of you shares an answer with the class. And then we'll talk about significant digits. Don't worry if the number looks kind of close to 10, okay? And you'll see why very soon. Anyone? Well,
10.6. I have 10.5708245.
look at that. Beautiful, Suzanne.
Okay.
That's exactly what the answer is. But you did say 10.6, which I like, because that's even better. So the calculator tells me that that's the answer. If I put it there, it's going to be okay, but I need to look at the significant digits. These don't count because these are exact numbers. These don't count because these are exact numbers. So even though there are 3 significant digits here, it really is an infinite number of significant digits. They don't count. The only thing that counts is your input, the number that was given to you as part of the problem, and that has 3 significant digits. The 2 zeros are significant because of the rules that we have learned. So you said, and I mean Suzanne, 10.6 quarts. And that I like, I think that's the right answer. Let me switch to, I'm not gonna switch you guys, I'm just gonna switch myself right now to see if there's one answer like that. It looks like there is. So at this point, I guess I can share that screen. I'm gonna see if I can do this desktop instead. So I don't have to be switching. If it's too small, you please let me know. But hopefully you see that I'm marking 10.6 quarts on the homework. Can you see my screen?
Yes.
Okay, great. So let's submit that as the answer. And it looks like that's the right answer. So we're good. Now let me go to the next problem. And now I'm gonna leave you to work on these problems on your own with a couple of suggestions. First, always use the conversion factors that your book has, preferably, if at all possible. If you end up using something else, let's see what the system does when you enter the answer. And if you get an answer that you think is correct, because you did it several times, because you checked with Wolfram Alpha, and you're still getting it marked wrong, all you have to do is tell me, and I'll look into it and give you credit for that answer. Now, let's see if we can actually tell verbatim. I can't believe that I'm doing this, but anyway. Put that in Wolfram Alpha. This is not cheating, by the way. This is knowing how to use technology to your advantage. I don't know if Wolfram Alpha is going to be able to process that much information, so let's see. Ah, it didn't like it, did it? No, it got all confused. That's a good thing, but we can actually rephrase this question into a question that Wolfram Alpha can handle. Because this first part of the question is a distractor. That has nothing to do with what you're being asked to do. The problem is simply asking you to convert that to pounds. Can you still read this? Is this too small? Hopefully that's bigger. So this is what I call, and many people do too, a distraction. It has nothing to do with the problem. I'm gonna get rid of that. And simply put it like that. So do I have an amount here in pounds? Well, first of all, I don't see it. Tell me if you guys see it. No, it's getting really confused. So it not always works. Let's see if I get rid of that. I'm gonna use the symbol for pounds. Oops. And see, oh, there it is. I don't even have to hit the return button. You see that? So 14.3962, 3 significant digits. What would that number be in 3 significant digits?
14.4.
Okay, so let's go back to the homework and see if there's a choice. Yes, 14.4. Let's submit it, and it looks like it's the right answer. Now, once again, you guys, I'm not trying to create shortcuts for you. I'm just telling you that once you are comfortable with using conversion factors, you should feel free to either double check your answers using, something like Wolfram Alpha, or once you really are super good at it, just do it with Wolfram Alpha. I mean, I know eventually you need these time savers, but please, let's do this problem just to wrap it up by hand. And do you still see my screen? Hopefully
Yes.
you do. Yeah, so this time I'm sharing my entire desktop, so I don't have to be switching back and forth between screens. So 6.53, we're gonna do the conversion of convert 6.53 kilograms to, it was pounds, right? To pounds. And for that, we need to look at the book to see what's the conversion factor of pounds to, oh, so once again, we need 2 steps because we have 1 pound equals 454 grams. We don't have one for kilograms. But you know that 1 kilogram equals 1,000 grams. So either we do it, oh, I'm sorry. See, that's one of the problems with not switching. So we have this from the book. We know this from the first part of the class. Is there a way of taking a shortcut? Well, with practice, you're gonna realize that to go from grams to kilograms, all you have to do is move the decimal point 3 places. In other words, I can take a quick shortcut here and say 1 pound equals 0.454 kilograms. All I did is I moved the decimal place 3 spaces to the left. But I did that because I already know that that can be done, and because I know that this is true, that 1 kilogram equals 1,000 grams. In other words, if I divide grams by 1,000, I get kilograms. I don't want to confuse anyone by saying this, but there is a way of doing it that way. So we're going to do it both ways because this is the last conversion that we're going to do, and then we're going to see how we get the same two results. So we're going to use this 1 second, but first we're going to do these 2 steps. 6.53 kilograms. We're going to convert that first to grams. So we need to choose a conversion factor from the bottom equality, the one that has grams on top, because we want to keep the units of grams. And then we're going to go to the second conversion factor and put the units that we want on top, 1 pound, and the units that we want to get rid of on the bottom, 454 grams. And now we're ready to check if our units are correct. Kilograms cancels with kilograms, grams cancels with grams. We are left with pounds, so we did it right. And if we carry out the math of that, we should end up with the same answer that we had before with Wolfram Alpha, which was, I forgot, 14.4 pounds. So let's see if we get that. Okay. Please always follow along with your calculator. It's important that you do that. I mean, this is where we can review whether or not you know scientific notation or how to use your own calculator. This is what I get on my calculator, 14.38. It's a slightly different number than Wolfram Alpha, as you can see. But when we round off, we end up with the same answer. Compare that 14.383 to the 14.3962, very different. And that's because they use a different conversion factor. They probably use 1 pound, oops, sorry, let me switch. They probably use 1 pound equals 454 point something, okay? But nevertheless, we get the same answer to 3 significant digits. Now let's do it with this shortcut, which comes from the fact that we know that we have to, in our heads, fix this conversion factor to have it in kilograms. So 6.53 kilograms. Now we choose a conversion factor from this equality and we put the units that we want on top. 1 pound divided by 0.454 kilograms. Kilograms cancel each other out and we get exactly the same answer. So that's taking a quick shortcut. With practice that can be done, but please keep in mind that the safest way to do it is just step by step by step. Takes a little bit more time, but it doesn't fail as long as you set it up correctly. But you can always check yourselves by doing the unit cancellation. Okay, so please feel free to ask questions if you have questions. Let me just go back to the homework and see what comes next. So this is another conversion. I'm gonna skip that. So I think we need to spend a little bit of time talking about percentages. Okay? The percentage can be tricky. Now let me ask you a question. Let me see who's left. Oh, the same 5 people. So we have here Selma, Amal, Matt, and Suzanne. Okay, perfect. So here goes a question for the 4 of you. If you saw that there was, we have the pandemic and you don't want to go to crowded places, at least I don't. I can assure you of that. I'm getting older in age and I don't want to risk myself. But if I heard that there was a sale somewhere and I really wanted to buy that item that is on sale, well, if it was 10% off, I probably wouldn't risk my health going there. But if it was 90% off, I would probably go. So can you guys use percentage in the sense of a sale very quickly? Yes, no, maybe. So 20% off, what does that tell you, Roselma? What is 20%? What is 20% off of a $50 pair of shoes?
Hold on, I'll tell you in a second because I actually coupon.
Oh,
$10.
yeah, there you go. So you can actually do percentages already. But we're gonna look at percentages today almost like a formula, okay? So don't change a thing if you already know how to do it in your head for certain things. But for chemistry, sometimes we need to think of percentage as a formula. So percentage means part per 100. If I were to write a formula for that, it's almost like a conversion factor. So percent, what did I do with my pen? Oh, here it is. Percent uses that symbol and is parts of something divided by the whole, whatever it means the totality, times always by 100%. So this is a formula in a way, because you have a numerator, a denominator, and then you have an equal sign. So a formula. Now, let's see how we use that type of formula. First, for a simple problem. Let me go back. Can I? Excuse me, I'm gonna sneeze. So I'm gonna, oh my God. I think I muted that right on time. I just hate to be listening to this presentation and hear the professor sneeze super loud. So just one quick second, you guys. I need to clear my... Okay. So we have here a question in using percentages. A penny is what percent of a dollar? I mean, this is common sense. How many pennies are in $1? Anyone? How many pennies in $1?
100.
100. So if we look at the formula that I have here, and the question is how many pennies are in $1? I mean, what percentage of a dollar is 1 penny? Well, we are asking for this part of the equation. We don't know it, but we know the parts. We have one penny. Okay? The whole is 100 pennies. You just told me that. So times 100%. So if you carry out that, you're gonna get 1%. That's your answer. And that looks complicated because we use a formula, but nevertheless it gets you the answer that you want by using that formula. Okay, so now let's look at a more complex situation. So here we have a problem in which we have a gemstone, a sapphire, that has 52.7% aluminum, 47.1% oxygen, and traces, meaning tiny amounts of titanium. Now, if you notice, if you add 52.7%, and I'm adding that as we speak, to 47.1,
99.8.
exactly, Iraselma. You don't get 100, you get 99.8. So the traces in this case is about 0.2%. It doesn't matter too much, except that you want to know that traces are a small number. Now, here we go with the question. If the sapphire or the stone contains this much oxygen, what is the mass of the whole rock, of the whole gemstone? Well, let's take a look at the problem using the formula that I just mentioned to you. And let me just copy some numbers here so that I have them readily available before I switch to my camera. 47.1%, and that's it. Okay. So ignore these for now. These numbers we're gonna need, and we're just gonna set up the formula. So percent equals parts divided by whole times 100%. Now you're gonna need a little bit of algebra here because you're gonna have to rearrange this formula. The question is asking you for the mass of the whole. So what is the mass of the complete gemstone? Using this information and this information. So we need to set up our problem carefully. This is what we want. We don't have it. We have that and we have that. So let's replace it in the formula. Here are the two numbers. This is the mass of oxygen, and this is the percent of oxygen. Which of those two numbers do you think is this number right here? Is it the 0.155 or the 47.1 that goes here?
47.1.
The 47.1, right?
Yes.
Okay, so we're gonna recopy this formula, but now with the numbers that we have, with all the information that we have. So we know that a gemstone of that type, a sapphire, is 47.1% oxygen. I'm gonna use the symbol just because we need to get used to chemical symbols. Equal, so there is an equal sign. Now, we know the parts of oxygen that represent 47.1%. In a 100 gram gem, 47.1 grams would be oxygen, but this one is clearly not a 100-gram gem. It's gonna be less than that. So we know the parts of oxygen, that goes here. What we don't know is the whole. So this is the gemstone. And then we have the 100% right here. So now the next task has very little to do with chemistry and more to do with algebra. We need to rearrange this equation so that whole is on one side of the equal sign and all of the numbers are on the other side of the equal sign. And since I'm not a math professor, I'm just gonna do it in my head, and forgive me for not showing you that. So it becomes something like this. Whole equals 0.155 grams of oxygen divided by 47.1% oxygen times 100%. So that's my rearranged formula according to my algebra. And now we just enter numbers in the calculator and we're gonna find the answer to that problem using percentage as a formula, as a conversion factor, if you will. And of course, you're gonna learn how to take shortcuts later. Now, before I put the answer, so the hole really means the sapphire. Let me ask you a question. If that sapphire is 0.155 grams in oxygen, is your answer gonna be a number bigger than 0.155 or smaller than 0.155? What do you think? In other words, are parts of the stone more than the whole of the stone or less than the whole of the stone? Anyone? So the whole should always be bigger than the parts. All of the parts are gonna add up to the whole, to the complete, if you will. So I would expect for you guys to be thinking, well, that complete stone should be bigger, more heavy than the 0.155 grams of oxygen. And I get on my calculator this answer. Well, let me show it to you so that I can then round it off as you're gonna tell me. So that's my calculator answer. But my input information has 3 significant digits. So how do I round off that number to 3 sig figs? Anyone? I see Amal trying to speak, but I didn't hear a thing. Sometimes the microphones fail. So I'm gonna assume, Amal, that you said 0.329. And then the units are grams. And that's the sapphire. So if we go back to the homework, is there such a choice? Yes, there is. It's right there. We're gonna say that's our answer, submitted. And we did it. So this, in a nutshell, is the idea of percentages as conversion factors. So we have one last topic to discuss today, and then we'll be pretty much finished with chapter 2. And that is the idea of density, which is another formula. It's another conversion factor. And it's actually part of a future lab, I think. So let me stop right here, go back to the book and talk about density briefly. Okay, just a couple of words on volume. So the volume of an object, when we meet face to face, we actually do this very nicely in lab. The volume of an object can be calculated in a number of ways, some of them more convenient than others. So for instance, one way of calculating the volume of an object is by using geometry, looking at the object, measuring the length, the width, and the height of the object, and then multiplying the 3 numbers. That will give you the volume of that, I guess it's a rectangular solid. But many times in chemistry, we need to calculate the volume of something that is not regular, that doesn't have a nice shape of a rectangular geometry. So when we do that, instead of measuring volume by calculation, we're gonna measure volume by displacement. So let me show you that. It's in the next section, I guess. So this is called volume by displacement. And it's a very nice technique that unfortunately, because we're not meeting face to face, we cannot do. But it works as follows. You get a graduated cylinder, which is a piece of glass that measures volume more accurately than a beaker or a flask. It has these graduations that allows you to see numbers a little bit more precisely. And you add some liquid. Most of the time, we simply add water. And then you add that liquid and measure the volume with nothing else except the water. In this example that you see on your screen, we have 50 milliliters of water. And now we have a stone. This one is, I guess, called jade, that we want to know the volume of. Impossible to measure and to calculate by calculation, by measuring. So what we're going to do is we're going to measure the volume of that gemstone by displacement. So we drop carefully the stone into the liquid, and the gemstone is going to push the liquid level up by an equal amount to that of its volume. So here we have a new volume after we put the stone inside the cylinder of 60.5. You see the difference? That difference is the volume of the stone, and this is called volume by displacement. So 60.5 minus 50 gives you 10.5. The volume of the stone then is 10.5 milliliters. And you didn't have to do any math. It was done simply by dropping it into the liquid. So that's an important concept to have, because when we do density, we often rely on volume by displacement to measure density. Now, please write down this formula somewhere, wherever you take notes or wherever you work problems out. Have it in a corner or have it somewhere available, because we're going to use it more than once. And this is the formula of something called density. Density is a property of matter. It's a property of matter that is called intrinsic. It's identifiable, is always the same for any sample of matter, regardless of the size of the sample. So the density of lead, for instance, is always a certain number. And it doesn't matter if you have 1 gram of lead, 50 pounds of lead, or 1,000,000 grams of lead. The density doesn't change. So in fact, density sometimes can be used to identify different chemicals, mostly metals, because they are part of their own identity. And density is defined as the mass of a sample divided by the volume occupied by that same sample. It has to be the same, not the same number, but the same sample. So you weigh a sample, you measure that in grams, you weigh that, you measure the volume of that sample, you measure that in milliliters or cubic centimeters, and when you divide the two numbers, you get the so-called density. So let's switch to my camera and put that formula, because I'm going to give you two formulas in addition to that. Let me just very quickly make sure that I know what your book uses for the word density, because when I was studying chemistry, we used to use a symbol called rho instead of what they do in this new book. I'm trying to find it. I don't see it yet. Come on. Well, believe it or not, I didn't see it. We're just gonna use big D, capital D. And I'll change it if it's something else later. Okay, I never saw it. So density we're going to call it capital D in this course, is equal to M over V. If the symbols are slightly different in the book that you're reading, or if you discover that it's not capital D but lowercase d, no big deal. But that's density, and we're going to learn all about it right now. Now, in the old chemistry books, density used to be called rho, which is actually like a big L from the Greek alphabet. We're just going to stay with capital D. The units that we mostly going to use are grams for mass and milliliters for volume. But you can also use grams and cubic centimeters, or you can also use, if you want, kilograms and liters, as long as the units are mass over volume. We could even use pounds per gallon. That would be valid. But it cannot be mass and mass or volume. It has to be mass and volume. Okay? Now, I'm going to give you 3 formulas just to save you some algebra. But of course, if you know algebra, you don't need to see what I'm going to write down. This is the formula for finding the density if you know the mass and the volume of something. This is the formula for finding the volume if you know the mass and the density. And this is the formula for finding the mass if you know the density and the volume. So density equals mass over volume. Volume equals mass divided by density. Mass equals density times volume. So with those 3 formulas, you can actually answer almost any problem that you're going to encounter. And let's just switch to some real cases from the homework, I believe. Okay, so let's take a look at this one. This one looks a little tricky. If the density of air is 1.29 grams per liter, which of the following is a unit factor? Okay, so let me switch to my screen. That's what the book is saying, that's the density, 1.29 grams per liter is the density of air. So can we actually come up with a conversion factor using density? And the answer is yes, because this is telling you the following. 1.29 grams of air equal exactly, there's an implied 1 here. You don't see it, but when you see per liter, and no number means per 1 liter of air. So the per any unit is per 1 of that unit. So that's actually a conversion factor. Let's take a look at the choices. Which of these can be considered a conversion factor? 1.29 liters per 1 gram? No. We actually are switching them. 1.29 grams per 1.21 liters? No, this is saying 1.29 grams per 1 liter. So 1.29 grams per 1 liter looks like that's the right one. This is not true, and this is backwards. So that should be your answer. So they are conversion factors in addition to properties of matter. Now we have a problem. And I'm going to let you try to solve it. Everybody's so quiet. I even wonder if you guys are still around. No, it doesn't matter to me. I'm just being facetious here. And I can't believe that this is recorded, but anyway, that's the way it goes. So here we have a 10 milliliter volume of mercury has a mass of 0.136 kilograms. What is the density of mercury in grams per milliliter? Notice the tricky part of the problem. Grams, kilograms. So I'll give you a minute and a half to try to solve this problem on your own. That's the way I teach when we teach face-to-face. I like people to try things before I show them how to do it. So in 1 minute and a half, I'll check with you and I'll start working it out. I'm not gonna put you on the stop. I'll just work it out, okay? 1.5 minutes, start now. Okay, I think that's about 1.5 minutes. So let me start working the problem out, and hopefully you had a little bit of a chance to set it up and compare what I'm gonna show you with what you did. If you have an answer, that's wonderful. Just don't share it with me yet.
Okay.
So the question is, what is the density of a sample of mercury given the volume and the mass of mercury? So let me switch over here and write density equals mass over volume. Now, the units of mass that the problem is giving us are kilograms, but they want the answer in grams. So we have two choices. Either we take the time to convert kilograms to grams the way we did it at the beginning of today's meeting, or we simply realize that by multiplying this by 1,000, we get the grams. And I'm just gonna do that. So I'm gonna, in my head, multiply this by 1,000, and I'm gonna write down that as the mass on the formula. So we have 136 grams of mercury. And then I look at the volume given to me in the problem, and the volume is 10 milliliters. So that is already in the units that they want, grams per milliliter. So I'm gonna put that amount of mercury in volume at the bottom of the formula. So 10.0 milliliters. And now I just do the math on the calculator, and I end up with 13.6 grams per milliliter. And I check my significant digits, 3, 3, 3. So that's gonna be my answer. Now, I just wanna show you something that you don't have to worry too much about, but sometimes you still encounter that, unfortunately, in some books. You may actually see something like this. Grams, milliliter, -1. If you see that, that just means pair. That means the -1 is telling you that the milliliters are in the denominator. You're not gonna see it often. You're gonna write it down like that. So if we go back to the homework problem, we see if there's one of the choices for us to pick. And there are, 3 of them that are very close together. Now, interestingly enough, these 2 choices right here are probably numerically correct if you flip the numbers. In other words, if you put the 10 on top and the 0.136 on the bottom, you probably get one of these answers. So those are distracting answers. The real answer we already know, we're sure of it, we're gonna submit it. Any questions about this problem? I feel like I'm going really slow, but then I feel like I'm going too fast. So you guys are gonna be my barometer. You're gonna tell me to slow down if I start going too fast. I never go too slow. I feel like I'm sorry. I never go too fast, but I may go too slow. All right, next part. These are conversions that we have done before, so I'm gonna let you do that on your own. I just wanna make sure that we have covered everything from chapter 2. So we covered conversion factors, converting from different unit systems, percentage, and now finally density. Okay, so this looks like a fun exercise for you to try on your own. Maybe you have done it already. This is actually, oh wow, what is this one, you guys? Let me look at this. Write the name of the metric unit indicated by the following symbols. So I don't have a problem with that. What do you think I should enter here, anyone?
Kilometer.
Right, I think I agree with that. Oops. I don't even know what happens if you spell it like the British. Let's see. What happens if I spell it like that? Oh,
Sorry.
it speaks British English. But this one is the one that threw me off. What is this A? Oh, atto, right?
Attogram.
Yeah. God, I forgot about that. I'm not even gonna look it up. So is it 2 T's for that? A-T-T-O gram? Like
Yeah.
that?
Yeah.
Atto is such a small amount that I never really, that and femto are super small. So anyway, enough said about this one. That one is easy to do on your own. You guys can do that on your own. This one looks like something fun that you can try also on your own. Stop me if you think I'm lying, or if you already tried the homework and you got stuck, okay? So that one also we can skip. We can pass that one. We can pass that one. That one. Setting up conversion units. I think you can do this on your own too. More practice with scientific notation. This one. I mean, there's plenty of problems here to be practicing your skills. So that's a good thing. I know it's a long homework, but it's required so that you can actually feel comfortable with these conversions. So that's why we spent 2 weeks on this chapter, okay? More conversions that you can handle now with what you practiced today. Same thing here. Those word problems, don't let them confuse you. Okay, so here we have one that we probably should try. And I think this probably will be the last problem that we solve together today. So we go back to present as a formula I'm writing it down on my piece of paper before I show it to you, but what we need to answer is if we have a solution with 335 milliliters of ethanol and 385 milliliters of water, what is the percent of ethanol in the solution? So I'm gonna put these two numbers on the piece of paper because I don't wanna be switching back and forth. And then I'll ask you a question about COVID-19 of H2O percent ethanol. Okay, I have the problem set up. So the problem tells you that you have a solution. A solution, as you're gonna learn in this course, is a mixture that is homogeneous. You don't see the different parts of the substances. It looks equal throughout. Now this one has two liquids that are clear, so you don't even know that you have alcohol until you smell it. But it has 335 milliliters of ETOH, that's ethanol, shorthand, and 385 milliliters of H2O, which as you know is water. And they want to know the percent ethanol in that solution, in that mixture. Well, how do we proceed? What we need to find out is here. We don't have that. So let's put it down here. Percent ethanol equals. Now, we have the parts of ethanol. We're given the amount of the parts of ethanol, 335 milliliters. So we're gonna put that verbatim, exactly as it appears on the problem. Okay? Now, the bottom is not given to us written, but do we have it? Can I have feedback from anyone? Do we know what is the whole? What number do, go ahead, I'm sorry, I'm out.
We're gonna add the water plus the ethanol.
That is exactly right. We're gonna add the water plus the ethanol, and that's gonna give you the total solution, the complete amount. So I don't even know what that total is, so I'm gonna have to add it up. You probably already did. I get 720. If I'm wrong, you're gonna fix it for me, but I think I'm okay. 720 is the whole, is still in milliliters, and then we put times 100% because we have to carry out that number to find the percentage. So we're all set. If we carry out this formula, we're gonna find the percent ethanol in that solution. And what is that? Well, 335 divided by 720. Times 100%. Don't forget the 100% right here. And on my calculator, this is what I get. But I'm gonna round it off to the 3 significant digits that my two solutions had. So it's gonna be 46.5% ethanol. Okay, I'm gonna switch to mastering and enter that 46.5 number. The percent is already given to me here on the right, so I don't need to add it, and I'm gonna submit that. And we got it right. Now here's a question for you. Could you use that solution to decontaminate something that you think may have COVID, well, actually it's called SARS, COVID-19, let's just call it like that. Do any of you know the answer to that question? Is that good enough? Come on, the pandemic is still going on, so is 46.5% 46.5% ethanol good enough to disinfect COVID-19? Okay, so here goes the answer. It's not enough. It has to be at the very least 70% ethanol or 70% rubbing alcohol, isopropyl alcohol. No less than that. I'm a paranoid, so I even use 75%. But 70% alcohol is what you need. All right? Just a little bit of extra information related to these crazy times that we're living in. Okay, any questions about that problem before I move on? Because we're almost at the end of the homework. The next one is another percentage problem. I want to leave you to do that one on your own with the formula that you have learned. In this case, you have the parts and the percentage, and you need to, hold on. Oh no, you are given the whole and the percentage, and you need to find out the amount of copper in the spoon. So you're gonna be doing some work that we haven't done together, but that I think you can do if you spend some time looking at the formula and setting it up right. So I leave that up to you guys to work it out. This one is just equivalencies. One thing that I should say is that 1 milliliter equals 1 cubic centimeter is something that is often overlooked, but is a relationship that you should remember. So 1 milliliter equals 1 cubic centimeter. So this is measuring volume by displacement. You can do that on your own. Here you had to calculate mass in grams given the density of some substances. So you're going to be using the formulas that I gave you earlier, one of those 3 formulas for density. And then finally, 2 problems more with understanding how density works. So, I have not asked you this question. With that in mind, with this problem in mind, can you tell me what is heavier? 1 pound of feathers or 1 pound of lead?
Lead.
Okay, so 1 pound of lead is heavier than 1 pound of feathers. Do you guys agree? Thank you for being brave enough to answer, but so I was trying to trick you. 1 pound of feathers is exactly the same weight as 1 pound of lead. The key word there is pound. Now, what you're thinking, and is what all of us think, is that 1 pound of feathers is gonna occupy a much bigger space because it's lighter. So lighter on quote than lead. Yes, lead is heavier than feathers, but if we weigh them, if we measure mass and we say 1 pound of feathers versus 1 pound of lead, they're exactly the same amount. Although if you look at the pile of feathers that you will see with 1 pound of feathers, it's gonna be much larger than the tiny piece of lead that is gonna weigh 1 pound. So I hope that you think about density and how density is a property. Yes, the density of lead is higher than the density of feathers, but the mass is the same as long as you're using the same units. 1 kilogram of feathers equals 1 kilogram of lead. All right, let's see, one last problem, which I think you can solve on your own with the formulas. I'm not saying that you won't have to think about it, but you can. And that's the chapter. That was chapter 2. So now we have a few minutes left that we can spend looking back at the lab. But before I switch to the lab, are there any questions from anyone? And at the end, we can talk about other questions that you may have about something else. So I'm going to close mastering. And I'm going to switch to the pivot assignment. Irasalma, I think you got it here after we were talking about one of the labs for this week. And we were beginning to complete this table on part 2 of the first lab. I don't want anybody to worry about getting this right. You just give it the best shot that you can. It's not exactly super intuitive or makes a lot of sense, but I do want to spend a couple of minutes here looking at the data once we finish measuring. So we're going to keep filling this table together and see what happens to the graph below. And then, of course, ask questions if you have questions. So that was the second measurement. Let's play the video for the third measurement. So it looks like we should stop it right there and take a look. What is the new volume here, you guys? I read it as 5150, probably 52.0. Would you agree with that?
Can you make
Yes.
it more bigger?
Yes, I can try. You mean like that?
Yes.
Very good suggestion. It's not really 52, is it? 51,
One.
51.8. I mean, remember that we are certain of the 51. I know it's 51 at the very least, right?
Yeah.
Let me switch to the spotlight. So I can see that it's more than 50, more than 51, is not quite at 52. So I am certain of the one. The next number that I'm going to write down is going to be a guess. And I'm just going to guess 0.8. You can guess whatever you want. It's not going to be wrong. So I'm going to put 51. Oops. 0.8. You can write 0.9. You can write 0.7. It doesn't matter. Now, let's look at the scale. 161.4. That's the liquid plus the cylinder. Remember that the balance wasn't third. So 160, what was it? 161?
0.4.
Or 164?
161.4.
Thank you. 161.4. So now to get this number, the liquid mass, remember that we need to subtract the 96.4 from the 161.4.
65.
What was it, 65?
Yes.
0.0?
Yes.
Okay. So now let's go back to the video. Play a little bit more. Okay, let's stop it right there. And what do you guys see?
68.
Okay, I can be certain of the A, yes. And it's probably 68.0. So I'm just gonna go with that, but the 0.0 is a guess.
Okay.
Okay? The 8 we are certain of, the 0.0 is a guess. Now let's take a look at the scale. You know, I hope the way I see it here is the way you see it on your screens, because that's one of the problems with Zoom. 182.1. So can you do the math, Amal, since you've been doing it for us?
85.7.
85.7?
Yes.
Okay, so 85.7 it is. And now let's take a look at, is that it for the video? I don't even know if they have more. Looks like, It's not playing anymore. So maybe that's it. So let's take a look at the graph. So it looks like a straight line,
Yes.
which kind of makes sense because we are measuring the density. You see how we measure the volume and the mass? With that, we can actually calculate the density of the liquid. In fact, we can take any of these two values, and this is where your algebra comes in handy. I'm not saying that you need to know it, by the way. This exercise goes a little bit beyond what I do when we do classroom work face-to-face. But it's beautiful to see that this is really algebra at work. This mass divided by this volume will give you the density of that liquid. This mass divided by that volume. This mass divided by that volume. You're gonna get essentially the same number because it's a straight line. Now, let's see what they say here. Now that we have found the mass and volume, we need to figure out the density. For that, we need to find, let me make it bigger, the equation for the line on your graph. So click the cog at the upper right of the graph. Okay, let's see that. That's the cog. And then what are we supposed to do with that? Select curve fits and choose linear. So we're gonna select curve fits and then choose linear. So we're gonna do that choice.
Yes.
And say done. Okay. So as we predicted, it's a straight line. And then let's see what it says. A line and equation will appear on the graph. And then it says, which part of the equation is equal to the density? Hint, y equals mx plus b, which piece would be equal to mass over volume. So what do you think is mass over volume?
M.
So the slope, m.
Yes.
Yes. So the slope of the curve is gonna give you the density of this liquid, which is gonna be the same number that you would have calculated by dividing this number by that number or this number by that number, except that this is using algebra. So now, in a different class, somebody asked me what happens after you submit. Can you change your answer? And apparently, the students are telling me that they can't. So if you get it wrong, at least you have a couple of attempts. Now, based on that information and looking at these numbers right here, what's the density of this liquid? So what's the slope?
$1.260. You have A equal. The slope is A in this one.
The slope is A in this case, right?
Yeah.
So 1.26 with that margin of error. So let's look at the table of choices to see what is our substance. So here we have a table with several densities. And remember, density is intrinsic. It's always the same, no matter the size of the sample. There's 1.26 here, and it points to glycerin. So we're gonna say glycerin is the actual liquid that we have. Let me mark corn syrup just to see what happens when I submit the wrong answer. Okay, careful, your calculated density should be smaller than what is required for corn syrup. Oh, that's a nice hint. So let's say glycerin, submit, and we got it. And then let's see what else is done here. We can use the density to calculate the mass of a liquid from the volume. Remember that a unit in both the numerator and denominator of a fraction cancels out. All right, so this is something that we talked about today. I think you can probably do this on your own and enjoy the exercise.
Yes.
So at the beginning, Amal, you had a question. Have I answered that question or?
Yes, but in the second lab, they told us to do 2 lines. I don't know how to do that.
Okay, so let's take a look at the second lab. Quite frankly, I haven't looked at it, so it's gonna be new to me too. Oops. It takes me to my professor thing. And we are Chemo 9.0. This one. Okay. I think this first part you can do on your own. Okay. Is it on on question 11 where I should start? Oh, no,
No.
not yet.
No.
Keep going, right?
Yes.
Wow, this is a long lab.
Yes. This one. It's
This
like the
one right here.
first one, but here they have 2 items.
I see, liquid 1 and liquid 2.
Yes.
Okay. So let's load liquid 1. So it's essentially the same as we did before.
Yes, the same.
And then there is a table. Okay, hold on, let me stop it. There's a table, trial, volume 2, trial. I'm trying to understand. Oh, it doesn't fit. So play and pause the video, see how upon record the mass of and volume at 5 different points for each trial in the table below. Okay. So what happens when you enter numbers here, here, and here for the first trial, and then you enter numbers here, here, and here for the second trial? Do you get 2 graphs or not?
No, you get just the points, but when you do the graph, he give you just one line, not 2 lines.
I see. And then using the graphing feature. Okay. Change it. So maybe that's what you're talking about here. Change the 2 axes so the fluid mass trial 2 mass is on the vertical axis. I see. So we can actually change that, right?
Yes.
And you did that.
Yes, I try.
And do you get a different line when you do that?
Don't think so.
Okay, so this may take a little bit longer than just a few minutes. So if anybody wants to leave, you are welcome to do so. But I'm gonna stay here with Amal looking at this exercise. Okay, Amal, just give me 2 minutes to drink a little bit of water and then we'll start filling on the tables and see what happens, okay?
Okay.
And I think at this point, maybe I should stop the recording because, I mean, if people have questions of this type, either they come to class like you guys did, I know they don't always have time, or they come to my office hours. Otherwise, this is gonna get really long for the recording. And we do have a limit of 2.5 hours, I think. So stop recording. Where? I don't even know how.